Hi, my name is Aisha Komaria Badria Binti alias. My matrix number is 07DKA23F2031. The calculation of slab 1 and slab 2 in reinforced concrete design follows a systematic process that ensures the slab can safely carry the applied loads. Although both slabs are analyzed using the same principles, the result may differ depending on their dimensions, support conditions, and loading. The first step in the design process is to identify the type of slab. This is determined by comparing the ratio of the longest span to the shortest span. If the ratio is greater than 2, the slab behaves as a one-way slab, where load is primarily transferred in one direction. If the ratio is less than or equal to 2, it is considered a two-way slab, where loads are distributed in both directions. This distinction is important because it affects how bending moments are calculated for both slab 1 and slab 2. Next, the load acting on the slab must be determined. This includes the dead load and live load. The dead load consists of the self-weight on the slab, which is calculated from the slab thickness, and the unit weight of concrete, as well as any additional finishes such as tiles or screed. The live load depends on the usage of the building and is usually specified in design codes. These loads are then combined to obtain the total load and further factored to obtain the ultimate design load using appropriate load factor. Once the ultimate load is known, the bending moment for the slab is calculated. For a one-way slab, the bending moment is typically determined using the formula, assuming simple support conditions. For a two-way slab, moment coefficients are used to calculate bending moment in both directions based on standard design table that consider the slab support condition. Finally, appropriate reinforcement is selected by choosing suitable bar diameters and spacing to provide the required steel area. The design must also satisfy the minimum reinforcement requirements specified in design standard to prevent cracking and ensure durability. Slab 2 is typically analyzed as a two-way slab, especially when the ratio of its longest span to shortest span is less than or equal to 2. This means the slab does not just bend in one direction, but instead distribute loads in both the X direction and Y direction. Because of this, the structural behavior of slab 2 is more complex compared to a one-way slab, as reinforcement must be provided in both directions to resist bending moments. The design of slab 2 begins with determining the loads acting on it. This includes the dead load, which consists of the self-weight of the slab and any additional finishes, and the live load, which depends on the intended use of the structure. After calculating both loads, they are combined and factored to obtain the ultimate load. This ultimate load represents the maximum load the slab must safely support under design conditions.
Hello everyone, for slab 2, we carry out the structural design following the standard Eurocode procedure. Our goal was to determine the required reinforcement and ensure the slab is safe. Step 1 is effective depth and reinforcement area. First, we calculate the effective depth for both the X and Y direction to account for the concrete cover. Next, we determine the minimum reinforcement area. Based on the concrete grade and the slab dimension, we found that the minimum area required is 180. This acts as our baseline. We cannot provide less than this amount. Step 2, mine reinforcement bending. We then calculate the required steel for the three critical areas: the short spans, the support spans, and the long spans. For all these sections, the calculated steel area was actually lower than our minimum requirement. Therefore, to be safe and complete with regulation, we decide to use H10-300 bars, which provide an actual area for 261. This covers all our bending requirements comfortably. Step 3 is shear check. Finally, we check if the slab could resist shear force. The maximum design shear force is 20.66 kN, we calculate the concrete natural shear resistance, which is 54.8 kN. We also check the minimum shear strength, which is 66.8 kN. Since our applied shear force is significantly lower than what the concrete can handle, no additional shear reinforcement like links is needed. The slab is structurally sound. Thank you. Moving on to the deflection check. We need to ensure the slab is stiff enough so it doesn't sag. We calculate the allowable span to depth ratio based on the reinforcement provided after applying the modification factor. Our allowable limit is 42.3. Our actual ratio is only 29.6. Since the actual ratio is much lower than the allowable limit, the slab passed the deflection test with no issue. Step 5 is cracking control. Next, we check for cracking to ensure the durability and appearance of the concrete. First, since our slab thickness is 165 mm, which is less than 200 mm, it automatically meets the basic requirement for crack control. We also check the maximum bar spacing. For the main bar, the limit is 375 mm. For the secondary bar, the limit is 450 mm. Our design uses a spacing of 300 mm, which is well within this limit. Therefore, the slab is safe for excessive cracking. Conclusion: in summary, slab 2 is fully compliant. It meets all the requirements for bending, shear, deflection, and cracking. Let's look at the design for beam 1. This is a continuous beam with a span of 8.0 meters and a cross section of 200 mm by 550 mm. First, material and specification. For this design, we use concrete grade 25 FCK, high strength steel 500 for both the main reinforcement and the link. We also assume a 30 mm concrete cover to ensure the beam is protect the environment factor. Step 2. Effection flank width. Because the beam work together with the slab, we need to calculate the effection flank width. This tells us how much of the slab actually help the beam carry the load. We calculate this for two different conditions: the end spans AB, CD, and the interior spans B and C. For the end spans, we use an effective width of 2120 mm, and for the interior spans, it was 1880 mm. This value are circular for calculating the beam strength later on. Step 3 is loading. Finally, the determine and total action or load acting on the beam. The permanent load, which include the self-weight and finish, total 1496 kN and variable load is 9.0. This load will be used in the next step to calculation the bending moment and shear force. Step 4. Design load calculation. After identify the action, we calculate the total design load using the Eurocode safety factor 1.35 GK plus 1.5 QK This results in a design load of 33.70 km. For the entire span, the total design force is 269.6 kN. For the main reinforce, we designed the reinforce for two different areas, spans A, B, C, and D. We checked the moment capacity and found the natural axis is within the flank. Based on this, we use 2H20 bar. Support B and C, the bending moment here is higher, 237.2 kN. Since our calculation K value is less than the cable, 0.167, no compression still is required. To handle the tension, we decide to use 5H20 bars, provide an area of 1571 mm. For the shear and force, lastly we check the shear resistance. We first ensure the concrete strut will not crash by calculating BR max at both 22 and 45 angle. The concrete capacity is much higher than our maximum shear force of 161.8 kN. To resist this shear, we design links. We decide to use R6-150 spacing. This ensures the beam is safe.
Hello, my name is Amira and my number matrix is 07DK83F2047. Today I will present beam 1. For beam 1, we started by identifying the type of beam and the loads acting on it. The beam is analyzed based on bending moment and shear force to determine the required reinforcement. Next, we calculate the maximum bending moment using the standard structural formula, which is M equal frac WL square over 8. From this calculation, we obtain the moment value which is used for designing the reinforcement. For the next slide is, after that we determine the required area of reinforcement based on the calculated moment and material strength. We also calculate the spacing of the reinforcement bar to ensure it meets safety requirements and does not exceed allowable limits. Finally, we check whether the design safeties the design codes and safety criteria. For beam 2, we calculate all the loads involved, including dead loads, live loads, additional loads if applicable. Then we determine the maximum bending moment using the same formula. This value is important because it determines the strength required for the beam. So based on the calculation on beam 2, we determine that the suitable beam size, the number and size of reinforcement bar, the spacing between the bars. We also ensure that all values are within safe limits according to design standard.
Next, the beam is analyzed to determine the internal forces, particularly the bending moment and shear force. The bending moment depends on the span length and support condition of beam 2. For simply supported beam, the maximum bending moment typically occurs at midspan, while the maximum shear force across the supports. These values are calculated using standard structural formula. Once the bending moment is obtained, the required area of tensile reinforcement is calculated. This is done by relating the bending moment to steel strength and effective depth of the beam. The effective depth is determined by subtracting the concrete cover and half the diameter of the reinforcement bar from the overall depth of the beam. Based on the required steel area, suitable bar diameters and quantities are selected to ensure the beam can safely resist the applied bending force. In addition to bending reinforcement, shear reinforcement must also be designed. Shear force is highest near the supports, so stirrups are provided to prevent shear failure. The spacing of this stirrup is determined based on the magnitude of the shear force, with closer spacing required in region of higher shear. After completing the design of beam 2, the load is then transferred to the column. The column is a vertical structure element responsible for carrying load from the beam and slab down to the foundation. The total load acting on the column includes contribution from beam 2, other connecting beams, slab, and the self-weight of the column itself. The column is then designed to safely support this axial load. This involves calculating the required cross-sectional area and determining the amount of longitudinal reinforcement needed. Vertical reinforcement bars are provided to carry the compressive force, while lateral ties or links are added to confine the concrete and improve stability.